today we have Inbar Savoray telling us about new physics from data.
Yeah, okay, hi. So, I haven't met before, so my name is Inbar. I started my postdoc at UC Berkeley a few months ago. And I'll try to tell you a little bit about this project, Learning New Physics from Data, Symmetrized approach. So the name is a little bit confusing, but that's sort of on purpose. I'll try to make it a little bit less confusing during the talk. So usually when I give this talk, I need to warn people that this talk involves statistics. So I hope nobody's severely allergic or anything like that, but I hope we can put through it together.
We only deal in absolute certainties here.
Absolute certainties, that's exactly what we should be doing. We're theorists. So this project was in collaboration with Shikma Bressler from Weizmann Institute and her student Yuval Zurgir, who just graduated. So I'll try to make these words a little bit clearer during the talk. Feel free to ask any questions whenever you feel like you have questions. Okay, so our motivation is basically the usual motivation. So we know that despite great theoretical and experimental effort, we haven't seen new physics yet. And there have been many very impressive dedicated searches that have done a really good job at ruling out a significant portion of the parameter space that is motivated theoretically or for theoretically motivated models. But we think there's still a lot more to explore. First, we probably still have more theoretical models we would like to consider. And we also have a lot more data that hasn't been analyzed and also that will be collected.
What about new signals? Do you think that there are regions of signal space that should be more explored? I know this is just your intro, but...
This is just the intro, but sure, yeah. I mean, so I guess that kind of goes under new theoretical models in some sense, but yeah, hopefully. Okay, so the idea is to kind of complement the dedicated searches with model-agnostic searches. So this is the framework is what is called a data-directed paradigm. So the idea is basically that instead of asking, is this a particular type of new physics model, we just ask, is this the standard model or not? So this is basically the question that we're trying to answer in the most model-agnostic possible way. And we do that by searching for deviations from known standard model properties. We would like to have a method that can scan the data efficiently because we expect to have a lot of data. And basically identify anomalous regions that can be later used for dedicated theoretical studies. So this is usually done with basically having some standard model simulation or some knowledge of the standard model and comparing it to our data. One property that we can test for that is kind of cool is standard model symmetries or approximate symmetries. So if we have, so we know that there are approximate symmetries within the standard model that imply certain ratios, certain relations, between different parts of the data. And if these relations are violated, we expect that new physics should explain them. So one example is lepton flavor universality. So we know that electrons, muons, and tau should be roughly interchangeable if the energy is high enough. So it's basically neglecting mass-dependent effects. So one question we can ask is, instead of is our data the same as the standard model simulation, we can ask, is our electron data the same as our muon data, for example. So testing for these symmetries is basically giving us a fully data-driven way of asking this question. So instead of working hard on producing simulations, we can just compare different parts of the data to itself. So that's the general idea. So again, our goal is to basically have an efficient method to scan for asymmetries between samples that we expect should be the same within the standard model, and then should only differ by statistical fluctuations. And we would like to have the interpretation of the results of this method to be as model independent as possible. So that goes both for the standard model and for new physics. So we'd like to make minimal assumptions and to try and not use any detailed simulations. So again, both for the standard model and for new physics. we would like a method that is fast and robust, again, because we would like to scan huge amount of data. And we would like to have a method that is very flexible, so it can describe many different types of new physics. So that is basically our goal. So we're going to ask the question, is the muon sample the same as the electron sample? This could be also phrased in a different way, but basically we can reduce it to the question, is this data sample coming from the same source as the other data sample? We'd like to do it in a fast, robust, and flexible way. Questions so far? The idea is pretty clear. Okay, so one way to start and approach this question is given by this series of papers here. So there are a few papers. The first of them was published by Andrea Wutzer and Raffaele, and I'm sorry, I'm probably not pronouncing the name correctly, but Raffaele will know. So these papers are called Learning New Physics from a Machine, or NPLM. And the idea in these papers is basically to test whether an observed data sample is distributed according to a much larger sample that came from the standard model. So that could be either a simulation or some other control region of the data. And in order to achieve these goals of having a fast and robust method that's also flexible, they're basically using the likelihood ratio test for the statistical test and using machine learning essentially for flexibility. Okay, so what we would like to answer basically in this talk is, can we use this method, or can we modify this method such that we can answer the question that is interesting to us, namely, is the electron data the same as the muon data? And the key difference here is that, as we will see, this NPLM method basically assumes that we have a much larger standard model sample compared to our data sample. But if we're looking for very small symmetry violations, we kind of expect also that the data samples are going to be of the same size. So if I expect muons and electrons to be roughly the same, then I don't necessarily expect a much larger number of electrons compared to muons. Turns out that this feature of having a much larger standard model sample compared to the data sample is kind of crucial for the NPLM method. So what we're trying to understand is, can it be modified such that we can implement it to search for small asymmetries between samples? So the plan is to kind of explain the NPLM method. So that would require explaining how they're using the likelihood ratio test and where machine learning has anything to do with all of this. We'll see the challenges that are the challenges of this NPLM method, and we will see how we can address them with our new formalism, which we call the symmetrized formalism. Okay, any questions about the plan so far, or complaints?
So,
yes.
the sample data should be from simulation or standard model. Otherwise, experimental data will have the same asymmetry as the data you want to test, and they will look the same, even if there's a symmetry.
So in our case, we really just want to compare two data sets, so two things that came from an actual experiment. Of course, it doesn't have to be the case. It could be simulation versus data. Maybe I don't fully understand the question, because I feel like I didn't address it fully.
So for electron muon,
Yeah.
electron data will be the large reference data, and muon data will be the data you want to test and see if it looks the same as it.
Yes, but so our approach would basically to not make one of them much larger than the other, because in real data they are not necessarily going to be imbalanced, right? And the question that we're really answering is, did these two samples come from the same distribution, or did they come from two different distributions? So this is like a symmetrized way of approaching that question, rather than, is the data sample distributed according to the much larger standard model sample?
If they are from different distribution, they are asymmetry.
Yes, right.
I did kind of have the same question. I don't know if you're going to cover it about the NPLM methods. For your method, it seems pretty clear. But if you were actually looking for new physics, I mean, the way you originally asked the question, since you can only ask whether the two distributions have the same statistics, right? It seems that one of them you have to, if you're trying to find an anomaly from the standard model, one of them has to be the standard model, which means that it has to be simulation, right? Because you don't know whether the data is
Right.
the standard model or not. That's the whole point.
Yeah, so that is a key point in our approach that is actually also in the NPLM method. So the point is that we don't know what the standard model distribution is, right? But we are testing the assumption that the muons and the electrons are the same.
So actually, in your case, it's more clear, but I'm still curious, like for the NPLM method as envisioned by these guys, and in fact, we had a talk by Danielo on this a long time ago, but I've forgotten the answer to this question. Is it only for comparing, is it only useful to compare simulation to data?
So,
Or
yes.
is there another way of using it beyond that?
So I actually think that our method is just a generalization of this NPLM method, so I hope that becomes kind of clear.
Yeah.
But yeah, my claim is, okay, maybe I'll just go
Just
through
why don't you go on
the
and we'll
slides,
see.
but
Yeah,
yeah,
maybe.
we probably address it. But in any case, so the idea here is that indeed we are unable to test if what we think is the standard model distribution is the same as what we see in data. The only thing we're testing here is to see if we have any difference between electrons and muons. That's essentially the idea. So we're kind of agnostic to, so in some sense the standard model is a nuisance parameter in this question, right? So we don't really care about whatever the distribution of the common source is, we just care of whether we see that electrons are different from muons. So, and that question can also be rephrased for when we have a simulation versus data, like the standard model versus some new physics. We basically only care about the differences between them, right? So this is why also this approach is kind of a generalization of the NPLM method, even though it kind of looks like they're answering different questions. And I'll go back to this point, so I hope it becomes like clear. Any more questions at this point? The next slide is going to be on statistics, so like, it's your best chance of kind of delaying that. Okay, not too much. Okay, so just like a brief reminder, I assume people have seen this before, but if not, feel free to ask questions, even if you feel like they're very basic. So let's just start by the definition of a likelihood. So a likelihood is of a model with parameters theta given some data x. It's just a probability of obtaining data x within a model with parameters theta. That's all it is. And we're going to use the likelihood both for model fitting and for hypothesis testing. Okay, how do we use the likelihood for model fitting? So the idea is that the model in which the probability of obtaining the observed data is the highest is the most likely. So we fit parameters by basically finding the parameters that give us the highest probability of obtaining the data. Okay? Right, so two things to kind of keep in mind. One thing is that the likelihood is always maximal if prediction is equal to observed, unless we have some other constraints. So the likelihood doesn't really know anything about true nature, it only knows things about our samples or our observed data. And it's going to try and best fit to our data, whatever it is. So this method is obviously prone to overfitting. Another thing to keep in mind, that we will kind of see later, is that if something occurred, it cannot have a zero probability. That's kind of a maybe trivial statement. So if we are fitting by finding the maximum of the likelihood, and we have something that's occurred, and in our model we actually have a zero probability for that event, we are not doing a very good maximization work, essentially, right? So if we got a zero probability for something that can go between 0 and 1, it's probably not that good of a fit. Right? So if something occurred, it doesn't really make sense to predict a zero probability to it. Okay, any questions on that? Okay. Okay, so just a very simple example. Let's say I assume my data came from a Gaussian PDF and I want to estimate the mean and the standard deviation, so x0 and sigma. So these will be my theta, my parameters. So what I need to do is I need to write the probability of obtaining my data within a model that its parameters are x0 and sigma. So this is just going to be a multiplication of Gaussian. So I just get this total probability there. And now what I need to do to find x0 and sigma is basically take the derivative with respect to x0, take the derivative with respect to sigma, and find where I get a maximum for the likelihood. So you can convince yourself by basically just doing this exercise that the best fit for x naught would be the sample average x bar, and the best fit parameter for sigma is just going to be the standard deviation of the sample. So that's not very surprising, and this is kind of also showing us a particular example that we likelihood basically is going to fit the observation to be exactly as the prediction. So we basically take averages on our sample. Okay. Cool. So how do we use this to do hypothesis testing? So we're going to use the maximum profile likelihood test. So what we would like to do is to test the null hypothesis H0 versus some alternative hypothesis H1. And they are going to be nested, meaning that the null hypothesis is contained as some subspace within the alternative hypothesis. So to be a bit more concrete, we can think of the null hypothesis as being the standard model, and then the alternative hypothesis will be standard model plus new physics. So if new physics is set to 0, then we get back the standard model hypothesis. So the way we're going to construct our test, so T is our statistical test. It's going to be twice the log, and then we take the best fit for the alternative hypothesis. So this is the maximal likelihood within the parameters, so within the parameter space of the alternative hypothesis, and we compare that to the best fit for the null hypothesis likelihood. So we take the maximum of the likelihood for H1 and divide it by the maximum of the likelihood for H0. And this is just going to be our statistical test. One reason to use this test is it's supposed to be optimal according to the Neyman-Pearson lemma. There are some subtleties to that, but we're going to ignore them for now. And what we're going to basically do is we're going to work in the frequentist approach. So what we need to do is we need to generate toy data sets from H0, calculate this T on these toy data sets, and get this distribution of the statistical test T. Then we take the result that we got, our T observed, and we calculate a p-value. So we just plug this, we just put this T observed on the simulated distribution, and we calculate the area from this point to infinity, let's say. I hope that's clear. Okay, so if you remember what we said at the beginning is that we would like to have as little simulations as we can, and this doesn't sound like it's going to have very little simulations because I need to generate toy data sets from my null hypothesis, and in particular the standard model hypothesis. So this doesn't really sound like it agrees with our philosophy. But the nice thing about the likelihood test is that if we have enough data, it approaches some asymptotic distribution that does not depend on the underlying model. So if I have a large enough number of data points, then the distribution of T will just approach a chi-squared, where the number of degrees of freedom is basically the number of degrees of freedom in the alternative hypothesis minus the number of degrees of freedom in the null hypothesis. So for the case that we are talking about here, the number of degrees of freedom in the chi-squared will just be the number of degrees of freedom of new physics. Yeah.
So what is phi T at?
So this is the PDF of the test statistic.
Test statistic.
Yeah.
T, it's the
It's
statistics of that thing up there.
Yeah.
Oh,
So
is phi a function? What is?
So this is just the PDF. Phi is just the PDF, the probability distribution density, the probability
Of
density
getting this T
function.
out of this H0.
Yeah. So this is
Okay.
T generated from data sets. T on data sets that came from H0. So these are the distribution if the null hypothesis was correct.
It's more likely to be incorrect.
So this is actually for just one parameter of interest. So this is for chi-squared of one parameter. But if you go to higher number of parameters, then this thing starts to look more like tends to a Gaussian, large enough number of degrees of freedom. But the idea is that if the null hypothesis is correct, then the numerator and the denominator are going to be roughly the same, right? So it's going to be but of course there are going to be some deviations from that, right? The best fit, even if the null hypothesis is correct, then best fit doesn't have to give us the null hypothesis. It could be some overfitting to noise or whatever. right? So we need to account for that fact. And the way we account for that fact in the frequentist method is by basically simulating this process of calculating t, right? So we produce parallel universes in which we conducted this experiment, and we find the p-value by taking the t that we saw and asking what's the probability to basically reject. So what's the probability of getting a larger disagreement than this if the correct hypothesis is the null hypothesis?
It's a little confusing because you've written it as a function of h naught, but of course it really depends on the parameters mu. It's just that you're assuming that the data is distributed according to the standard model,
Yeah,
or
according
h
to
naught,
H naught,
right?
yes.
And then you're computing this thing which is looking for the new physics. That's
Yeah.
the distribution of the thing.
Uh-huh.
That,
Yes. Yeah. So since we know that we basically approach to a known distribution, we can hope to skip this step of simulating over and over and over, because this distribution should be independent. So it should be independent of the details of h naught if we have enough data, and also go to something that we know, so we don't need to estimate. So that would be the ideal case, in which we basically don't need any simulations at all, because we can just assume that it goes to a chi-squared. So then all we need to do is to calculate t on our data set, and we calculate its p-value from whatever tables of chi-squared. Or we ask Mathematica to calculate the area under the grid. Okay. Okay, so this is what's going to help this method be kind of fast and robust. So this is how we're going to hope to skip simulations, but we're going to test whether we can actually skip the simulation step. Okay, so now for the fun part, why do we use machine learning, and how does this relate to all of this? So we don't really need to be machine learning experts, and I am definitely not a machine learning expert, even after working on this project. Because for us, the machine learning part is really just a choice of fitting functions. So instead of using a polynomial or a complex set of functions, we're using a neural network, essentially. So a neural network is really just a specific choice of functions that are very expressive, and they're often referred to as universal approximators. Right? So that is the advantage of basically we don't need to know much, and we gain a lot of different distributions from it. The process of training is basically to find the parameters of this function. So the parameter of the functions are going to be the parameters of the neurons inside the neural network, and we find them usually by minimizing sum loss. So just a very quick overview. So each neuron is doing some linear operation and then acting with a nonlinear function of our choice. And some people can show that if you have enough layers, or if you have enough neurons in one layer, then you can basically approximate any continuous function. So this is why these functions are called universal approximators. So the parameters theta are just going to be basically the parameters of the linear combination within each neuron, and we usually choose the activation function, so the nonlinear function, ahead of time. So these parameters are just going to be found by minimizing sum loss. So the fitting is just minimizing whatever this is. So how we're going to use it here. So basically our neural network is just going to give us the PDFs in our model, which are also just the likelihoods. Right? So instead of having P of X be some polynomial, it's just going to be the output of a neural network, where the parameters are the parameters of the neural network. So that just gives us a very flexible function for P. So that gives us basically a way to account for all possible models approximately. So we're going to find these parameters theta by maximizing the likelihood, right? So if we define the loss of the neural network by minus the likelihood on the observed data, then what will happen during training is that we will try to essentially minimize the loss or maximize the likelihood. So the parameters are just going to automatically give us the maximum likelihood estimators. So then we can just use these to calculate our T. Okay, so this is there is no fancy pre-training or any complicated thing. This is really just a choice of a function. I input a data point x, it gives me the probability p. Okay? Is it maximally
You had
confusing
to-
or?
I mean, it sounds like it's just a way of fitting,
Yes,
it's just a way of fitting the
that's all it
data.
is.
That's it, right?
That's all it is,
Yeah.
yeah. We're not doing anything on simulation or anything, we're really just using all of our data because we want to find the parameters by maximizing the likelihood on data that we saw. So it's really just a way of doing a fit. That's supposed to be pretty flexible.
How long does it take for it to learn how to do that?
To learn how to do it or to run this?
To learn it?
To learn to use the tool or for the network to
For the network. Network
okay.
has to adjust itself to produce
Yeah, yeah,
the
yeah.
correct.
So we use the parameters that the NPLM guys used, which also involve a tiny network of only 4 neurons. So you can really simply analytically write what that function is. It's just a sum of basically 4 hyperbolic tangents or something. And we use the learning rate that they said, which was like 10 to the minus 3. Anyway, so it took so we ran it for 500,000 epochs, which is considered a lot usually in machine learning. And the reason for that is that we really just want to get to the maximization over the data. We don't want to have a rough approximation. We kind of really want to find the maximum likelihood. Yeah, so this is considered relatively slow, but it's so something like that usually took us. So depending on the biggest data set that we had, it would take like an order of like an hour or something to run for each toy data set.
How big a data set is that?
So this was for 200,000 points. And you can probably do some tricks to make it faster, but yeah. Any questions?
So I'm still thinking, where does the electron and muon data come in?
Right, so I'll explain it. So the next slide is going to be the NPLM case, and so I think it will become a bit clearer exactly how we use it. But ask again if you feel like that's not answered. Okay, more questions? Okay, so let's start by explaining the NPLM method. So again, the NPLM method wanted to test whether some data set A is drawn from the standard model distribution or from standard model plus new physics distribution. So we basically write our H0 to be the NDF, so the number density is given by the standard model prediction or by standard model plus new physics. This is completely generic. We're using the profile likelihood test, as we just mentioned, and they assume that the likelihood is Poisson likelihood. So basically, the number of events in my data is not fixed, right? So it can vary too. Okay, so we haven't specified what any of these things mean yet, so we kind of need to start doing that. So the first assumption that they use is basically parameterizing the new physics plus standard model as some reweighting of the standard model distribution. Okay, so the standard model plus new physics is just e to the f times the standard model distribution that we haven't specified yet. And the machine learning part comes in f. So f is just going to be the output of a neural network. Again, instead of being a polynomial or a Gaussian or whatever, it's just going to be the result of a neural network. And these parameters are going to be found by maximizing t, essentially. So if we knew what the standard model best fit was, then all we need to do is to find f, and we do it by maximizing t. So we still don't know what the standard model distribution is, but we kind of took care of the standard model plus new physics.
So this is, when you say comparing standard model with new physics, I have a feeling you don't mean a specific new physics model.
Right.
This is just any new physics.
Yes.
So this is really something different, because before we were always talking about standard things where you're comparing two definite hypotheses, right?
Yes, so this is any new physics. So this is basically testing the null hypothesis versus anything.
Okay.
This is not very well, yes.
Okay.
But we are going to do that so we're going to have a well-defined number of parameters, because these parameters come from the neural network. So this includes whatever the neural network is able to give us. Which could be very...
So you're assuming that you have learned the standard model. Is that how I should think of it? I'm sorry, I'm kind of, feel like I'm maybe losing the thread a little bit here.
So we want to test standard model versus standard model plus new physics. We haven't specified where the standard model distribution comes from yet.
Right.
We're just
Okay.
Yeah.
So it's magic, right? For now, it's magic.
For now, for this slide, it's completely magic.
Yeah. Okay.
Yes.
Okay.
Okay. Can anybody see a slight issue with this parameterization? Should really have the Jeopardy music.
You mean the parameterization? You mean just reweighting the events by
Yes.
e to the f of x?
Yeah.
Looks okay to me. I have to say, I don't know.
Okay, is it always okay?
Oh, I see. It's if some of the n's are 0, right? If some of the standard model are not populated at all,
Yeah.
right?
Then we have some problems, right? So if the standard model prediction is
Yeah.
0 somewhere, then this parameterization is not very well defined, right? So this is going to have some problems if the new physics prediction is in a background-free region of the standard model, which is often sometimes we do want to look at.
I mean, that also says that if you're interested in even very rare events,
Yeah.
you better have them, you better know them very well,
Yeah.
right?
Yeah, yeah. So this basically means that this is going to be very susceptible to whatever
Yeah.
f is. Yeah,
So
f is
if
going
you
to.
find background-free events, then you don't need any statistics.
Yeah, that's true, and that's what you expect to also get out of this method. Yeah. Yeah. So keep that in mind. But I mean, this choice kind of makes sense if we are looking at very small modifications to the standard model. Again, up until the point when we get to very small predictions for the standard model, or 0 prediction. Okay. So far we only dealt with the standard model plus new physics part. Let's now try to explain where the standard model distribution is coming from, because that's the other ingredient that we need. So usually the idea is that if we have a much larger sample of the standard model, we just take it and we perform a fit to it, and this is what we will stick here and there for the standard model distribution. This should make kind of sense. Basically we would expect to have some fit for the standard model distribution. But the shortcut that was taken in this paper is by saying, okay, in any case, I kind of assume that I have a much larger standard model sample than my new physics sample, for example, because I have a simulation that I can run as many times as I like versus my actual experiment. So maybe we don't really need to fit, but we can just take the sample to be the standard model prediction. So if my sample tends to infinity, then the distribution of the sample should give me exactly the distribution that it came from, right? If I have, and this, assuming this is unbiased, blah, blah, blah. So if I have a large enough sample, instead of calculating this integral over some analytic function that I fit, I can just use a Monte Carlo summation. So I can just use the empiric observation. So instead of instead of doing the integration of some known analytic function, I forget about finding an analytic function and just take the sum over the observed sum.
So the fact that you want B to be larger than A is because you want to be able to neglect fluctuations in B?
Yes.
Because, I mean, in practice, I think it's often done the other way around. Like, for example, you might have a sample of jets from Z's, and that's a very controlled sample that you sort of know are normal jets, and then you might want to compare, then use the statistical properties of those to compare to other jets. But there it's the other way around. Your sample is much smaller and you have to be
Yes.
wary about so you could in principle generalize this to try to take into account the errors in B.
Yeah, so one way to generalize is to say, okay, I don't know B exactly, and then I can have some nuisance parameters for and have some uncertainty on these parameters. Yeah,
Okay.
that's one thing we can do. But what was chosen for the NPLM paper is really just substituting the null hypothesis prediction is to be exactly the observed standard model sample.
Mm-hmm.
Okay. So then what I'm left with, this T, is really just given by something that summed over sample A something else with sum over sample B. And we said basically that the only thing that is unknown now is F. So I can find F by asking a neural network to maximize T or minimize minus T. Okay? So now we have a loss function for the neural network, which is just minus the likelihood ratio. And f of x is going to be the output of the network. So it's going to vary the parameters within the neural network such that we're going to minimize the loss or maximize the likelihood. So how do we interpret this? So the neural network is just giving us f of x. So wherever f of x is non-zero is somewhere that the neural network decided that we have new physics, basically, right? That we have a deviation between standard model and standard model plus new physics. And the significance of this result is obtained by calculating the p-value of t, which is just minus 2 times the loss of the neural network. Okay? So the process is basically, we have a data sample A, we have a much larger reference sample B. We ask a neural network to find f by minimizing this loss. Okay? And f is the exponential weights that indicate modifications or reweighting of the standard model distribution in this approach. Okay, any questions on this? This is just the NPLM method.
It's still magic where you get the standard model distribution, right? But
So
you're
the
going to
standard model
explain that.
distribution, here it's completely not magic. This is, we have a sample B that
What is-
represents the standard model.
How do you know that B is the standard model, whereas A might not be? I mean, is it,
Yeah, no, that's a good question. So
okay,
one thing you can do, and this is what basically was assumed here, is that you have a simulation of the standard model.
okay, sure.
That's one thing. But still, B is just a sample from the standard model. But here they assume that since B is large enough, we can basically treat it as an exact representation of the standard model distribution. Okay. Okay, so there are two main challenges of this method. So the first one, this was also noticed by the authors of the paper, is that the loss is actually unbounded, which is usually not a great thing. So if I have some point x star that exists only in sample A, but not on sample B, and f of x goes to infinity on that point, then the loss goes to minus infinity. And our neural network is going to be very happy because it was trying to minimize something and got minus infinity. So good job. Okay, so why would this happen? So this is really just a result of a false null hypothesis. So remember that our null hypothesis was that the distribution, that the standard model distribution or the common distribution of the two samples was the exact observed distribution of sample B. So if sample B had no events somewhere, then this model predicts a zero probability for these events to occur, right? But if these events did occur in sample A, then we just get exactly the undefined situation that we had before. So we basically predict a zero probability for events x star, and now we have to deal with the fact that the standard model plus new physics might not predict a zero probability for these events. So essentially the infinity that we get from the loss is really just a result of dividing by zero, which is not a very surprising fact.
You could also say that you have neglected the fluctuations in B.
Right, exactly. So this could come
Right.
from just neglecting fluctuations in B, right? So we can easily think of an example in which sample A and sample B both came from the standard model, but we had some events in sample A that did
Right.
not occur in sample B, just by fluctuations. So this is really just a wrong null hypothesis, because it predicted a zero probability to something that occurred. So the infinity here is completely physical. It's completely true, and it just indicates that we chose the wrong null hypothesis to what we are trying to test. Right, so in this case, we want to test whether sample A and sample B came from the same source, but we might get like an infinity significance for rejecting this hypothesis, even if it was just some statistical fluctuation. So even though this result is, it makes complete sense, if we want to use this to test whether sample A and sample B came from the same source, we need to modify this somehow. So the way that it was modified in the NPLM method is by introducing a weight clipping parameter. So this is a regularization method essentially setting a maximal gradient for the functions that we are looking at. So this is setting maximal weights. So very roughly, we can say that it's going to forbid divergences on small scales, and the parameter of the weight clipping is going to tell us what the size of the scale is. So this is generally a good idea. So this basically means that we are not going to be too sensitive to single data points, roughly, right? So we're going to try to forbid this from happening by saying, okay, my function cannot go to infinity on just one point, assuming that the points around it are going to occur in sample B2, or something like that. So this is, you can think of it as some sort of a binning almost thing. So we're basically smoothing things out, hoping that that will help us not overfit. Okay, so, but now we introduce another parameter that we need to set, the weight clipping parameter. So what is this maximal weight that we allow? So the weight was determined in the NPLM paper is kind of a clever idea. So the idea is that we said that we know that if we have enough data, then we expect the null hypothesis distribution of t to approach a chi-squared. So the conclusion from that was that if we don't get a chi-squared, but we have a large number of data points, then we should probably regularize. So the criterion for choosing this maximal gradient was set such that we can get something that looks like a chi-squared, because if we are away from a chi-squared, we're probably overfitting. Okay, so what you would need to do is to generate the distribution of t from your null hypothesis, see how far it is from a chi-squared, do this again with another weight clipping, do this again with a different weight clipping until you reach a chi-squared, and this is going to be your weight clipping parameter that you will use on your actual data. So this has two issues. The first is that, of course, the stricter the weight clipping is, the less flexible our network becomes. And the second thing is that, as we said before, we kind of wanted this chi-squared property to avoid the need to use many simulations. So what we're doing now is simulating in order to get to a chi-squared. Right? We now basically need to simulate again and again and again to find this weight clipping parameter, to have a good agreement with the asymptotic distribution. So we kind of didn't get rid of the need to simulate again and again with this method. So just to explain what we're seeing at the bottom. So on the right-hand side, we had sample B be 100 times larger than sample A. They both came from some exponential distribution. And this is the distribution that we get for t when A and B came from the same exact distribution. So we see that we have some deviation from the chi-squared that we expected here. And we also got roughly 2% of these tests to be divergent, right? So we got that minus infinity loss. Here we set the weight clipping parameter to 9, and we see that we get a good agreement with the chi-squared and also no training, so no data sets gave us an infinite test. So this regularization scheme works, but it has some disadvantages. So now we need to, again, simulate from H0, and we are also limiting the freedom of our network, essentially. Okay, that is one challenge. The other challenge, which is very relevant to what we're trying to do, is that this method requires a large ratio between the sample sizes. So it requires our samples to be very imbalanced. So if we set the weight clipping parameter to 9, we see that if the ratio between the size of sample B and the size of sample A is 100, we get this chi-square distribution. This is how we picked this number. But now if the ratio between the samples is 10, we see that we start to deviate from the chi-squared. And if the samples are exactly of the same size, we get a completely smeared thing that doesn't look like a chi-squared at all. So this means that we, again, are losing this property that we really like. We are losing this asymptotic property. It's going to be very dependent on the ratio between the two samples. And we actually found that this was more, depended more on the ratio between the sizes of the samples than on the overall number of events that you had. Yes?
Are you not allowed to change the weight clipping?
Yeah, so you can change the weight clipping, but that would just mean that you need to pick a different weight clipping for every ratio. And it looks like the further you are from sample B being much, much larger than A, the more strict your weight clipping is going to have to be. So you're losing this freedom more for samples that are closer in size.
I mean, to me, it looks like you're just asking a different question. I mean, here they're trying to use one very large distribution as a proxy for the true part of probability distribution, whereas you're trying to take two pretty much equal sized data sets,
Right.
not assume anything about what distribution they're coming from, and just ask, are they coming from the same distribution?
Yes.
To me, that just looks like a totally different question.
Yeah, so
You shouldn't have any of these
yeah.
issues. It's just a different question. I don't know, maybe I'm misunderstanding, but.
yeah, yeah, that's a good
And a much better defined one, by the way. I like your question much better than this, because this seems crazy. Where are you ever going to get, this just seems kind of nuts.
Yeah. So you're right. In their mechanism, you basically assume what the standard model distribution is, and that is the thing that goes wrong.
That's the thing that's nuts, seems like nuts to me.
Yeah. So like
Yeah.
that's the thing that just goes wrong when.
Yeah.
Yeah. And I think that the way that we approach this question is again more general, and it does reflect what they're trying to do, because they are coming up with this weight clipping thing. To kind of make up for the fact that they're using their own hypothesis, in some sense. But yeah, you could
Well, I want
try
to
and
see
handle
what you're
it in
going to
other
do.
ways.
Can you tell us what
Okay.
because I think that
Of
looks
course,
much
yeah.
more better, not crazy. It looks not crazy.
It looks not crazy, yes. Okay, so our proposal is, we call it the symmetrized formalism, which is my fault and it's completely not a good name. So the idea is that, again, instead of asking the question, is sample A, does sample A come exactly from the distribution of sample B, we really are just asking, are A and B coming from the same distribution or not? And we're going to answer this question in a symmetric way. So we're going to account for the fluctuations both in sample A and in sample B, because they are both samples. None of them is a theoretical calculation. Both of them, like in both cases, we're trying to deduce this distribution from data. So we're going to see that using this approach, we basically have an improved sensitivity for any ratio between the sample sizes, and we avoid these artificial singularities that we had before.
You could use this for simulation, right?
Yes.
One of them could be
Absolutely.
simulation. It would still be better than the other thing.
Yes, absolutely.
Okay.
Yeah. So how do we think about this? So in our case, we're basically so our null hypothesis is that sample A and sample B came from the same distribution, which we do not know. The common distribution denoted here is P naught. The null hypothesis, the alternative hypothesis is that sample A came from one distribution A, and sample B came from another distribution B. Okay? So what we're trying to do is to learn the common PDF from both samples and test the agreement of both samples with that distribution. So we're going to use this, the maximum likelihood test, but now we're doing it on both samples because they are both just samples. So in the null hypothesis, I only have one distribution that I need to find, and I'm going to find it such that it gives a good agreement with the combined sample A and B, right? This just comes out by writing these hypotheses into our profile likelihood test. And in the alternative hypothesis, I'm allowed to vary the distribution of A separately from B. Okay?
So PA and PB, just I want to make sure I'm following. PA and PB are literally just the probability for each event.
Yes.
It's a list of probabilities for each event. That's
Yeah,
all.
I mean, we want it to probably come from one continuous function.
Sure,
blah, blah,
sure,
blah, but yes.
but in principle, that's what it is in this expression,
Yes.
and you're going to minimize,
Maximize the likelihood.
that, yeah.
Yes, yes.
Right.
Indeed. And the difference between the null and the alternative is that in the null hypothesis, we only have one distribution describing both of them, and in the alternative, we have one distribution for A and one distribution for B. Okay. So again, we're going to learn the common P naught from both samples and test its agreement on both. So that is to kind of contrast with what was happening in the NPLM test, and now we can show that the NPLM is really just a private case of the symmetrized formalism. So if sample B was much, much larger than sample A, as was the case for the NPLM method, then it's going to dominate the maximization in the denominator, right? So the sample A plus B is very, very similar to sample B if sample B is huge compared to A. right? So then the common distribution is going to be roughly the distribution of sample B. So we can roughly cancel out the B terms, right? Because the fit to sample B is going to be roughly the same as the fit to A plus B. And now we're just left with a test on sample A of the best fit to sample B versus the best fit to sample A. So, and this gives us exactly the NPLM case, where the small addition in the NPLM case was that the best fit for sample B was exactly sample B. It was an exact overfitting of sample B.
Yeah.
So in that sense, these questions are actually the same. So
I think you're being too modest. This makes way more sense than what they did. I think you're being too modest. Okay.
yeah, that made sense to me. But so and this also explains why the NPLM test requires a big ratio between the sizes of the two samples, right? Because if the ratios of the samples, of the sizes of the samples is not big, then we're basically not doing a maximum likelihood fit. And this is why we get...
And the whole need that they do their clipping thing is because you can never really assume that B is infinitely large. That's the problem. And so you just take into account the fluctuations.
Exactly.
And of course it's much better.
Yeah, so, exactly. So this is much more natural in the sense that we don't know what the distribution is. And the null hypothesis says that both samples came from the same distribution. So they both should be used to determine what the distribution is. So if we had, and as we said, if we had something occur, it doesn't make sense to assign a zero probability to it, right? So this is going to take care of that too. Any more questions on this? Okay. So now we still need to specify how PA and PB and P naught are modeled. First of all, we're going to use something similar to the NPLM test case, even though this is not necessary. But we're going to say that A is just e to the f times P naught, and G and B is e to the G times P naught, where F and G are both going to come from neural networks. Okay? So this is similar to the NPLM case. So if you remember, we had a problem with this parameterization when P naught gave us 0 on events that did occur. So in the NPLM case, this P naught is really just chosen to be the observed distribution of sample B, right? But a more natural choice, which actually gives us the true global maximum for the null hypothesis, is to take the observed distribution of sample A plus B, right? So if what we had before is an overfitting to sample B, we will now have an overfitting to sample A and B together. This is the maximum likelihood possible.
So can I ask a question? So if my data was a bunch of counts, as is typical, if I had some bins and each bin just has some number of events, each one of those things is Poisson distributed, and I just had 2 of these distributions, then couldn't I just do this for one bin? Like for one bin, the only question I can ask is, well, what's the expected number of events in that bin? And now the data, they won't be exactly the same, but I can assign some kind of improbability or whatever, to this. Like if they're both small within fluctuations, you see what I mean? And so I can just do this problem once for one bin. It's the usual Poisson type trick.
Yeah.
I can do it for one bin where I'm literally just doing a single Poisson thing. Then I just multiply them together for all the bins.
Yeah, so
that should be equivalent to what you're doing is more general because it doesn't assume anything about Poisson. But in the Poisson case, which is the one that's easiest to think about, that is what you're doing.
So
is that right?
The difference between these two things is that basically your choice of fitting functions is stepwise functions. So it's just a bunch
Well, yeah, I'm
of
assuming that the data is God-given in some bins, which is not the case. In general, it's a continuous function, and so this is going to depend on the binning, and that's always a drawback in Poisson.
Yes.
But it's incredibly simple now, right?
Yes. So So you can do that. So again, this is more general, and so what you're doing when you're binning, you're effectively applying a filter, right?
Yes.
And this is a different type of filter, but So this is going to also be sensitive to.
But then I don't think I've understood, what is the role of your P naught? P naught is some reference?
So P naught is the common distribution that, so for, it's just a distribution that the null
Okay.
hypothesis comes up with.
Okay.
Yeah. So we could fit this distribution, or we can use the NPLM trick, but just on a distribution that makes sense. So the NPLM trick is to take the observed distribution of the sample, but they did it for sample B, and we propose to do it on sample A plus B. That's not the only thing you can do. But unlike the NPLM case, this is going to be completely generic. Because we now don't have any events that occurred in sample A, but didn't occur in A plus B, right? So we no longer have a problem of P not being 0, where NA wouldn't be non-zero, for example.
So I have to go to this other thing. Are you going to be around 3:30 for a little bit at least?
Yeah.
I'll come and look for you.
Sure.
Just a little bit after 3:30, after my thing is over, because I want to ask you some more questions.
Sure.
I'll stop slowing you down now. Thank you.
That's okay. No problem. Okay, so the result of what we now have is we have two independent test statistics, one for sample A and one for sample B. So both of them look exactly like the NPLM test. Instead of having sample B in this left sum, we have sample A plus B. So we're basically comparing data A to the combined A plus B and data B to the combined A plus B. And we're finding G and F as a result of a neural network. So now we have these two independent tests. We could also run in parallel. And we no longer have problems with divergences. So going back to this point again, we had divergences for the NPLM case when there was a point in A on which F went to infinity that did not occur in B. But now such points just do not exist, right? We do not have a point in the sum over A that do not exist in the sum over A and B. So we are the main reason is that we are no longer assigning a zero probability to events that did occur. So we don't have to deal with divergences because everything is, because our null hypothesis is not ruled out, essentially. Okay, so the next thing would be to show that this actually works. Any questions so far?
Is this test down here the loss you were describing earlier?
So this is the test, and minus that would be the loss. Yep. I hope I didn't write this down incorrectly, but that's...
They look pretty simple.
If the signs don't work out, let me know, because that's in the paper. But yeah. Okay. More questions on this idea? Okay. So now we can show that this actually works. So we tested it on toy lepton flavor violation example. So we had a sample of events that had an electron and a muon with opposite charges. Here they're ordered by their PT. So the momentum, the transfer momentum of the electron was larger than the transfer momentum of the muon. And we have roughly 200,000 events. Our X that we kept mentioning was just the collinear mass in units of 100 GeV, just to make these numbers order 1. So these are the hyperparameters of the network that I mentioned before. So in the symmetric case, we had A and B both randomly sampled from this EMU sample. And in the asymmetry case, we also added a Higgs lepton flavor violating decay to one of these samples, in this case to sample A. So this is to kind of emulate a search in which you would in principle compare an EMU sample to a MUE sample, right, to test if electrons and muons are the same. We just need to interchange them. And one signal that you can find in this way is, for example, a Higgs decay into tau E, and then the tau goes into muon plus things. So we expect some asymmetry in the energy or in the momentum of the electron versus the muon. So in our case, A and B really came from the same source, whereas in a realistic analysis they might not be entirely the same, but this is the toy example that we are testing on. Okay, so just to show that what we said kind of works, I think when I saw these plots I was, let's say, in maximal happiness throughout my PhD. So here we see again the cases where sample A and sample B have a ratio, so NB over NA is 100, so sample B is 100 times larger than sample A, sample B is 10 times larger than sample A, and on the bottom they are all the same size, which is the case we are mostly interested in. And we said that if we have enough data, we expect to get a chi-square distribution. That is the gray plot. And now we see that even with applying no weight clipping at all, we get distributions that are much closer to the chi-square distribution. So here we basically applied nothing and got back a reasonable agreement with the chi-squared for all these ratios. And we also had no divergences to deal with, because as we said, our method is unable to produce these divergences. They were really just artificial before.
Why does the top left one look worse than the others?
Good, that's a good question. So one thing is that in these cases, so here there's a sample that's 100 times smaller than the other one. So we think that the deviations come from the fact that we really just have a very small sample. Right? So
so the total data size is fixed?
So here the size of sample B was 200,000 and sample A was 100 times smaller, so 2,000 events. Whereas here it was 100,000 and 100,000. So almost the total the total is not the same by a very small fraction. But so we think that this is mostly because you basically have a small sample. Like one of them is a small sample. But there also could be some dependence on the ratio in a non-trivial way. But this seems to be consistent in most cases.
How do you think your total data is you generate them or you really get it from the HC?
So we're cheating. So we take a data from simulation, but we also assume that it's going to be the analogous case for collider analysis would be to compare mu data to mu e data, and that could have some asymmetry.
So the data you simulated.
Yes. So we simulate the data, but
you simulate with really LHC then or just random simulate?
So we simulated. So we used the simulation that was used for a different paper, but basically using MapGraph and Delphis for the detector, nothing too detailed though. And we also did not account for the fact that mu and mu e could be different within the sound model because of detector effects. So they both came from the same thing. Yeah. But this is simulation. Yeah. This is not actual data. Okay. Any more questions? Okay. So as we saw, there are some deviations from the chi-square distribution. So maybe you don't really want to count the result of a very predictable background-only distribution, even without a detailed standard model simulation. And the method we use is basically permutations. So again, the null hypothesis was that sample A and sample B came from the same source. So we can basically simulate the null hypothesis by taking sample A and sample B, combining them into a big sample, and then dividing that sample into two randomly again. And do that again and again and again. So we can use our own data to simulate the null hypothesis distribution. So we don't need to run a full simulation of the standard model. We just need to take our observed mu sample, our observed mu e sample, combine them, redivide, combine, redivide, combine, redivide. And we see that that gives us a very good approximation for the distribution that would come from an exact knowledge of the standard model distribution in this case. And again, this is the case because we are really just testing a symmetry hypothesis. So it doesn't really matter where the symmetry came from. Where by doing that, we're also kind of taking into account the particular features of our data. So this is something to do if you're not fully convinced by the chi-square, but you also don't really want to run a whole simulation of the standard model. And that gives a very good approximation. Okay, so the last thing is to see what happens when we have a signal. So all of this was for the null hypothesis distribution. So now we see that we can do better than the NPLM test. So on the right we have the NPLM test with a weight clipping of 9, set by essentially making sure that the distribution of the null hypothesis test statistic is a chi-squared for when sample B is 100 times larger than sample A. And here we see so we injected a signal with a growing number of signal events, and we wanted to see what the measured significance is with our procedure versus the NPLM procedure. And this is plotted as a function of the injected ideal significance. So this is the result of a test that knows exactly what the distribution of the background is, and the exact distribution of the signal is just looking for the height of the signal. So this is just to have some axes that we can compare these to. So we basically see that we get a lower detectability threshold by using our method, where when the samples are, so when sample B is much larger than sample A, we get roughly the same results. And when the samples are the same, we get that our method is much more sensitive than the NPLM case. The dashed lines are the chi-squared approximations. So we also see that our method is closer to the chi-squared case compared to the NPLM. And again, for our method, we did no weight clipping, no optimization. Okay, and the very last thing is to try and ask how sensitive our method is for a signal that we care about. So again, this is a very rough estimate. So we know that the current bound on Higgs-2 tau E is roughly 0.2%, both from ATLAS and CMS, and that was for a luminosity of 138 inverse femtobarn. For our method, we get that the sensitivity is roughly to a branching ratio of 2.6%, but at a luminosity of 10 inverse femtobarn. So if you believe a square root of L scaling, you essentially get that our method would give something around the 0.7 or 0.8%. So it's a factor of few worse than the current analysis, but we basically used no information of the underlying distribution to do that. Like we didn't design a very complicated analysis. We just threw everything into our mechanism and got a decent result. Yeah. Okay. So this is basically what I wanted to tell you. So we saw that standard model symmetries can be exploited for model-agnostic searches for new physics that are fully data-based. So we're comparing the data to itself, and we're trying to use simulations as little as possible. So we discussed the NPLM method, which was a method to test for deviations of an observed data set from a much larger reference data set. And we saw that this method had some challenges that are solved by the symmetrized formalism. So we are basically having a symmetric statistical test where we're accounting for fluctuations both in sample B and sample A, and we have a null hypothesis distribution, null hypothesis PDF that makes sense. So we're no longer assigning zero probability to events that did occur. And we show that this method is really just a generalization of this NPLM idea, and it allows us to test for differences between samples of arbitrary sizes and relaxing the need for tuning the model parameters. So really, while we were motivated to pursue this question from a standard model symmetry point, so looking for lepton flavor violation, this can really be used for anything. So even for comparing simulation to data. So any case in which we have two samples that we want to know if they came from the same source or not. Okay, maybe I'll end by just a few points for further, for future work. So now we want to make this more appropriate for realistic analysis. So including more than one variable would be probably a good idea. We also now need to account for systematic uncertainties and specifically for imperfect symmetries. So we know that detector effects basically treat electrons and muons in different ways. So the electron is different from the muon when they reach the detector. So we need to actually account for that fact if we really want to test the standard model. If we just want to test whether the electron sample is different from the muon sample, we can do what we proposed, but then we will also detect asymmetries that we know are part of the detector, for example. So the next step would be to take these effects into account. And this is already being handled within so Shigma's group had some works on that, and it was incorporated into the Atlas search. So now we want to try and incorporate that into our method. And we also are interested in thinking of improving the robustness of this method by preventing overfitting. Okay, and with that I will end, so thank you.
Questions?
So at the page before the summary, you say the branching ratio is like 2.6 at this luminosity. Will it be better if you use 138 luminosity?
So it's 2.6 at 10 inverse from the 1.
Yeah.
And we saw that we have roughly a square root of L scaling, square root of luminosity scaling for the sensitivity, for the branching ratio, sorry. Yeah, so roughly you should divide this number by the square root of the ratio between the luminosities to predict roughly what we're going to see, but this is an estimate.
I'm not good at calculating square root 2 in my head, but I guess.
It's a square root of 13.8.
But it will improve if you go
three,
higher
four.
luminosity, but it's just too costly for simulation. Well,
It's just, sorry?
like it costs too much computation power, that's why they're...
Yeah, it's a much larger number of events, but yeah, you could, yes. Yes.
So with this being totally model agnostic, I mean, like, the LHG is something where we've done like a whole lot of work on what the model might look like. Are there other experiments that you think this could be promising for, where we're much more open on what the model could be?
So again, this can be used for anything, really. You're asking about specific applications. So yeah, we only really thought of this in the context of the LHC, but it can work for other things. I know that, so some people asked us if we can do that for galaxy distributions or some things that we really have way less idea of what they look like. I suppose the answer should be yes. It could also be interesting to look on like other, so both astro and particle experiments, but this is pretty generic. So.
Well, there's a lot of Ben's question. You gave examples of point models. If there's anything, any direction you think physics lies in regions you look elsewhere that seems that have similar problems in physics, whether it's cosmology or anything other.
Yeah. So the direction of lepton flavor violation was once more motivated when the anomalies maybe were a bit more promising. Still worth looking there. Shikma had some thoughts of trying to do this for looking for CP violations. That's kind of a straightforward thing to look for, because they're kind of looking for some symmetry. But I don't know that it's totally motivated by a particular model.
You do also want some correlating data set between two known like standard model results, like like for example the electron thing, not just standard model versus experiments.
I mean, this could also be done for just standard model simulation versus experiments. But yeah, I think the strength of this method is when you don't want to get into the details of what the underlying distribution is, and you just want to use data.
Right.
If you have a very good model, use that model. Like, that goes both for the standard model and for the new physics. If you're looking for something that you feel is the new physics, do a dedicated search for it. This will give you a much weaker sensitivity.
Well, okay, so since I mentioned earlier that for the flavor violation that's used simulation of the LHC data, you mentioned you had 2.2 times 10 to the 5th
Yes.
data points from the electron. How many data points is actually from LHC? It's way more than that.
Yeah, so the number of data points that we had corresponded to roughly 10 to 10 instrument of iron. So the scaling would be, so this was, I think the 10 instrument of iron was the 2. I could be missing by a factor of 2, because I keep doing this exercise in my head and I keep getting it wrong. Up to a factor of 2, that is the 200,000 events. So it's either 100,000 events or 200,000 events.
200,000. Oh, okay. So realistically, how many
how many points can
Yeah, how many
can you have? So it could. So the current data is for 138 inverse line. This is the data that Atlas and CMS
Oh.
analyzed. So a factor of more than a factor of 10
I see.
larger. Yeah.
Well, not a technical limitation. So,
Yeah.
Okay, let's thank Inbar again.